So today we're diving into some sources you shared about the future of autonomous intelligence, specifically these new breakthroughs in large language model agents.
It's a really exciting space. We're seeing a shift from models that just answer questions to what the sources call deep research agents.
And what does that mean exactly? A deep research agent.
I mean, we're not just talking about retrieving facts anymore. These are models that can autonomously build new knowledge. They reason. They use external tools like the web, databases, code interpreters to figure things out on their own.
And they're designed for these long horizon tasks. That's the term they use.
Right. Tasks that require sustained reasoning, planning, maybe hundreds of different steps or interactions to get to a final answer.
That's sort of the holy grail, isn't it?
Right.
But there's a problem, a big one. The sources say that the current tech it hits a wall.
It really does. It's almost counterintuitive. The longer the task goes on, the worse the performance gets. The system just seems to break down.
So what's the flaw? Why does asking a smart AI to think for a long time cause it to, seize up?
Well, it all comes down to memory. And the solution we're looking at today is a new paradigm called IterResearch. It's designed to fix this very specific weakness in how agents currently remember things.
Okay, let's unpack this then. What is this weakness? What's the specific breakdown that IterResearch is trying to fix?
It's something the researchers call the monocontextual trap.
The monocontextual trap.
Yeah. The standard way these agents work is they take every piece of information they find, every reasoning step, every tool output, and they just append it. It all goes into a single, ever-expanding context window.
So it's like trying to do research by writing everything on one infinitely long piece of paper, and to remember anything, you have to read the whole thing from the beginning.
That's a fantastic analogy. And that scroll, as you call it, gets so long that two fundamental failures start to happen. The first one is pretty intuitive. They call it context suffocation. As that history fills up the context window, the actual space the model has for its current thinking, its active reasoning, that space shrinks.
So it's not that the AI gets dumber, it's that the room it has to do its actual work, its mental scratch pad, is getting crowded out by all the notes from before.
Precisely. It's forced to make shallow or premature conclusions because it's literally running out of room to think.
And the second failure, you said there were two.
The second one is maybe more subtle. It's noise contamination. When an agent is searching the web or exploring, it inevitably picks up junk. Irrelevant facts, dead ends, maybe even its own early mistakes.
And in the old model, that junk just stays there forever.
It's permanently embedded in the context, so that noise starts to interfere with everything that comes after, diluting the quality of the actual signal the agent needs to solve the problem.
So if linear accumulation is the problem, IterResearch must be doing something. Iterative. Nonlinear. How does it break free from that context wall?
It totally rethinks the process. It models the research task as an extended Markov decision process, or MDP.
A Markov decision process. For anyone who needs a refresher, that's the idea that the future only depends on the present state, not how you got there.
Exactly. And that's impossible if your present state includes every single thing that's ever happened. The key innovation here is what they call strategic workspace reconstruction.
Okay, strategic workspace reconstruction. What does that mean?
It means the agent's state, its memory, stays at a constant size. It doesn't grow over time. We go from a complexity of OT, which grows with every step, to just O1, constant.
A constant size. How do you fit a potentially huge 500-step investigation into a fixed size memory?
Because that memory, that state, only ever contains three things. First, the original question you asked it. That's static.
Okay.
Second, the immediate context, so the very last action it took and the tool's response. And third, and this is the absolute key, is something they call the evolving report.
The evolving report. This is the compressed memory, right? The synthesis of what actually matters.
It's the linchpin of the whole system. The LLM is actually really good at this stuff, naturally summarizing, compressing, filtering for relevance. So as part of its decision-making loop, it generates this report. It takes the raw, noisy search results and distills them into a clean, high-signal summary.
So it's constantly updating its own internal textbook on the problem.
That's the perfect way to think about it. And this leads to strategic forgetting. When the agent moves to the next step, it deliberately throws away the full history. The raw data, the intermediate thoughts, all gone.
All of it.
All of it. The only thing that gets carried forward is the knowledge inside that newly synthesized report. This is how it maintains that constant memory size and avoids both suffocation and contamination.
Here's where it gets really interesting for me, though. If you're forgetting the whole history, How do you stop the agent from just going down the same rabbit holes it already explored, say, 20 steps ago? Doesn't it need to remember its failures?
Well, that's the beauty of it. The information about the failure isn't lost, it's just compressed. So the report might have a line that says, searching for X was a dead end, we should focus on Y instead. The noise is gone, but the lesson learned is preserved. It forces the agent to constantly ask, based on my clean summary of what I know right now, what's the next best move?
That makes a lot of sense. So you're always working with high-quality insights, not raw data. But that brings up another challenge. If you have two paths to the right answer, one takes 5 steps and one takes 20, how do you train the agent to prefer the shorter path?
That is the exact problem they solve with the reinforcement learning part of this. It's called Efficiency-Aware Policy Optimization, or EAPO.
EAPO, okay.
Normally, in reinforcement learning for these tasks, the reward is just binary. You either got it right or you didn't. A 1 or a 0. Doesn't care if it took you 5 steps or 50.
So you need some way to push the agent to be more efficient, to prefer being concise.
And they do that with a classic technique called geometric reward discounting. Instead of just giving a reward of 1 at the end, they apply a tiny discount factor for every step taken.
Can you walk us through that? How does a small discount create a big push towards efficiency?
So the formula is pretty simple. The reward for any given step is the final reward. Let's say it's 1 multiplied by a discount factor, gamma, raised to the power of how many steps are left until the end.
Okay.
Gamma is set really close to 1, like 0.995. So for a single step, the discount is tiny, but it's multiplicative. Over a long task, it adds up. An action taken early in a short, successful run gets a significantly higher reward value than the same action in a long, meandering run.
So even though both paths get to the same answer, the training process gives more credit to the steps in the shorter path.
Precisely. The sources give an example where, for the same early step, the reward value can be almost 8% higher in a short path versus a long one. And when you do that over and over again in training, it creates this really strong pressure, this gradient, that basically teaches the agent, be focused, finish faster.
And the results back that up.
They do. The study showed that EAPO cut down the average number of steps by about 5.7%. And it did that while either maintaining or even improving the final accuracy. It really trained the agent to be disciplined.
Okay, so let's get to the empirical findings. The theory is great, but how does this actually perform on real-world benchmarks?
The gains are, well, they're substantial. Across 6 really complex data sets, things like GAIA and Humanities Last Exam, IterResearch saw an average improvement of 14.5 percentage points over the best open-source agents.
14.5 points is a huge leap.
It is. And in some cases, it's even closing the gap or outperforming some of the big proprietary systems. And you can trace the improvements directly back to the 2 failures we talked about.
Right, context suffocation and noise contamination.
On tasks that need a lot of web searching, the gains come from beating suffocation. On really complex reasoning tasks, the gains come from beating noise contamination because the agent is always working with that clean, synthesized report.
But the real showstopper here, the thing that really stands out in the sources, is the interaction scaling.
Oh, absolutely. This is the breakthrough. The old models top out at, a few dozen interactions? They choke.
At IterResearch,
They scaled it up to 2048 interactions, 2,000. And they did it using a pretty standard 40,000 token context window. It's just structurally impossible for the old paradigm to do that.
Wow. And what happened to performance when they gave it that much more room to explore?
It skyrocketed. On one task, accuracy went from just 3.5% when it was limited to only a couple of interactions, all the way up to 42.5% when it was allowed to go to 2048.
So what we thought were incredibly hard problems for AI might not have been hard because of the reasoning.
It seems they were hard because the agents were running out of breath. They didn't have the capacity to do enough exploration to find the answer. IterResearch gave them that capacity.
And one last thing, the sources say this works even without all the fancy training. It can just be a prompting strategy.
That's right. If you just take the structure, the idea of an evolving report and periodic synthesis, and apply it as a prompt to a powerful model, you still see massive gains, up to 19.2 percentage points better than the standard React prompting method.
Which proves the benefit is in the paradigm itself, not just the specific model they trained. It's a better way for any LLM to handle long reasoning chains.
It really solidifies the idea that this iterative synthesizing approach is just fundamentally a better way to do deep, sustained reasoning.
So what does this all mean for you, the learner? The essential difference here is a shift away from just accumulating a linear history and toward a cycle of iteration and strategic synthesis.
That's the core of it. The big contributions are this IterResearch paradigm, the EAPO training method that rewards efficiency, and then demonstrating this just unprecedented scaling and model-agnostic prompting power.
I want to leave you with a final thought on this. Building on what they found about efficiency, the researchers trained the agent with a hard cap of only 32 steps. They forced it to learn to be efficient. And yet that same agent, trained for discipline in that small space, was the one that could then scale up to over 2,000 steps.
The discipline strategies scaled gracefully.
Right. It suggests that the key to unlocking this kind of unbounded AI exploration might not be just giving them infinite memory. It might be about training them to be incredibly disciplined and concise with the memory they already have.